Engineers Newsletter live broadcast on energy-saving opportunities for LEED and the Energy Policy Act. I'm Jeannie Harshaw from Trane's Applications Engineering Department, and I'll be your host today. Before we dive into today's broadcast, let's cover some of the housekeeping. Through our association with the American Institute of Architects, credit towards continuing education can be earned for viewing today's broadcast. If you are an AIA member, make sure you provide your member number to your local host before leaving today's session. In several states, this certification can also be applied to engineers' continuing education requirements. Please check your state's rules to see if this might be applicable. The industry is certainly seeing an increased focus on energy reduction. Some of this is motivated by the rising cost of energy. As energy prices rise, investment in energy efficiency gets more attention. Some of this interest is due to increased environmental or social awareness related to issues like global warming, energy independence, or protecting natural resources for future generations. In addition, the green building movement has successfully directed more attention toward the efficient use of energy in buildings. Finally, in the U.S., legislation has created various tax incentives to promote energy efficiency. For example, the Energy Policy Act of 2005 allows a commercial building owner or leaseholder to claim a tax deduction, up to $1.80 per square foot, by making their building more energy efficient. This deduction, which was originally set to expire at the end of 2007, has been extended through December 31st of 2008. In order to claim this deduction, the U.S. Internal Revenue Service requires that the energy savings be certified through the use of computer modeling. Trane's Trace 700 software is one of several simulation programs that has been approved by the IRS for this certification. One of the opportunities that we'll talk about today is that if computer modeling has already been completed for a LEED project, the added work to document the energy savings for this tax deduction is pretty minimal. Whatever the motivation, this increased interest in reducing energy use in buildings creates opportunities for us in the HVAC industry to deliver solutions. According to the U.S. Green Building Council, buildings account for 39% of the energy used in the United States. Similar reports indicate this to be 33% in Canada and 17% in Mexico. So on this broadcast, our technical experts will discuss several energy-saving strategies to implement for various types of HVAC systems. And they'll quantify the impact of each toward achieving LEED points under the Optimize Energy Performance Credit. In addition, these same strategies may help the building owner qualify for tax deductions through the Energy Policy Act. Following the presentation, we'll answer some of your questions, so please fax them in at any time to the number on your screen. To cover this information today, we have three presenters. A familiar face is John Murphy. As an applications engineer, John's primary responsibility is to help customers with the design and application of HVAC systems in buildings. As a LEED accredited professional, he has helped our customers and local offices on a wide range of LEED projects. Joining John are two new faces to the E&L broadcasts. Matt Biesterfeld is the manager of Trane's CDS department, where he's responsible for overseeing development, support, and customer training for the Customer Direct Service, or CDS, products, including software tools such as Trace 700. He's also a member of Trane's Advanced Engineering Support Program, where he's responsible for building load and energy studies, including LEED, 90.1, EPACT, and performance contracting analyses. Also joining us today is Neil Maldiz. Neil is the manager of Trane's Energy Engineering Department. He's responsible for Trane's performance-based contracting on a national basis. We have a lot of information to cover today, so John, would you get us started?
Interest in the U.S. Green Building Council's LEED rating system is certainly growing, with a lot of support from different industries. Currently, the USGBC has more than 14,000 members and nearly 50,000 LEED accredited professionals. And as you'd expect, there's been a similar growth in LEED building projects. There are over 6,000 projects registered under LEED NC, with nearly 1,000 certified buildings. There are LEED projects in all 50 states and in 41 countries. During that same period of growth, we've had several E&L broadcasts devoted to LEED. In 2004, we produced a broadcast that reviewed the LEED NC prerequisites and credits that specifically relate to HVAC systems. Then the following year, we had two broadcasts. One reviewed the changes to how refrigerants are evaluated for LEED projects, and the other explained the specifics of performing the whole building energy analysis in order to achieve points under Energy and Atmosphere credit number 1. Finally, last November, we produced a different type of broadcast, where we reviewed 3 LEED projects in a case study format. Today's broadcast is in response to requests from many of our customers and field salespeople. We'll discuss energy-saving strategies to implement for various types of HVAC systems, and we'll quantify the impact of each toward achieving LEED points under the Optimized Energy Performance Credit. While the May 2005 broadcast got into the specifics of how to perform the analysis, today's broadcast will focus on what strategies to analyze for different system types. While there's been an increased interest in LEED overall, a somewhat recent change has brought more attention to this Optimized Energy Performance Credit. As of June 2007, all LEED projects are required to achieve at least 2 points under this credit. For LEED NC, this is Energy and Atmosphere credit number 1. There are 2 ways to achieve points under EA credit 1. The first path is the whole building energy simulation approach. This involves using simulation software such as Trace 700, Energy Plus, or eQuest to model the proposed building and compare it to a baseline building that is defined by ASHRAE Standard 90.1 2004. The rules for this analysis are defined in Appendix G of that standard. Then, points are achieved based on the percentage of building energy cost savings. So for a new building, to achieve the 2 mandatory EA Credit 1 points in LEED NC, the overall energy cost of the proposed building must be 14% lower than that of the baseline building. Note that the basis for comparison is overall building energy cost, not the efficiency of an individual piece of equipment. So this does not mean that every piece of equipment must be 14% more efficient. Rather, it means the overall building needs to be 14% more efficient. Now, you can also achieve points under EA Credit 1 by following one of 2 prescriptive approaches. One is the Advanced Buildings Core Performance Guide, which was developed by the New Buildings Institute. The other approach involves complying with the criteria established in the Advanced Energy Design Guide series. This is a series of guides that have been jointly developed by ASHRAE, the AIA, the Illuminating Engineering Society, the USGBC, and the U.S. Department of Energy. To date, there are guides for small office, small retail, and K-12 school buildings. And just last week, the guide for small warehouses was completed. 4 EA Credit 1 points are awarded if the project fully complies with all applicable criteria recommended by the appropriate guide. The first step is to locate the correct climate zone. For example, the Department of Energy has identified 8 climate zones for the United States. Each is defined by county borders, and the counties are listed next to the individual climate zone maps in the guide. These climate zones are based on temperature, and in some cases are subdivided into subzones based on humidity. While these guides are targeted at the United States, ASHRAE 90.1 uses the same classification for climate zones in many other countries. Since these climate zones are listed in an appendix of 90.1, these guides certainly could be used outside the U.S. Next, each guide includes tables that list the specific energy-saving recommendations by climate zone. By implementing all the recommendations listed, the project can achieve 4 EA Credit 1 points. Now, these recommendation tables represent some, but not all of the ways to reach the energy savings target. Their intent is to provide prescriptive guidance for saving energy without requiring the whole building simulation approach. Electronic versions of these guides are available for free download at the website shown on a previous slide. But our focus for today's broadcast is on the whole building simulation approach. Now, to minimize overall building energy cost, design teams should use a holistic or integrated approach that considers the interaction of building orientation and envelope construction with lighting and HVAC systems. For example, improvements to the building envelope and more efficient lighting systems both reduce the building cooling load, which often has the added effect of reducing HVAC energy costs. First reduce the load, and then design an efficient HVAC system. Now, while we could fill a whole broadcast talking about these types of strategies, I'll mention a few of the big ones that design teams should investigate, whether it's a LEED project or not. Minimize glazing, which faces east or west. Shade exterior glazing. Use insulating low E glass, and make all glazing as small as possible. Design the building envelope and glazing so the sun provides interior lighting at the perimeter of the building, a concept called daylighting. Then design efficient supplemental interior lighting that modulates when it's not needed. Finally, design and construct the exterior enclosure to be as airtight as possible. These and other ideas are discussed in the ASHRAE Green Guide, the Advanced Energy Design Guides, and in ASHRAE's new Guide for Buildings in Hot and Humid Climates. Now, while all LEED projects are encouraged to use this holistic design approach, we know very well that there are many projects that use the traditional separation of architecture and engineering activities. In this case, the mechanical engineer is often given the assignment to achieve EA Credit 1 points, sometimes without being able to change these other building elements or systems. So the first part of today's broadcast is meant to help the engineer identify which energy-saving strategies to consider for different HVAC system types. Matt, why don't you explain the analysis your team conducted for this broadcast?
Sure, John. We used Trane's Trace 700 building analysis software to model an example 270,000 square foot office building. As required by LEED NC, the baseline building was modeled according to Appendix G of ASHRAE 90.1, with 25% of the baseline building energy cost attributed to plug loads. For a building of this size, Appendix G requires the baseline to be a chilled water VAV system. The energy rates used for this study were the state average prices that are published by the Energy Information Administration. For the proposed building, we modeled 5 different HVAC system types and determined the impact of various energy-saving strategies. And we did this for 4 different locations in the U.S. Houston in the south is a hot and humid climate, so it's fairly representative of the southeast. Los Angeles in the west is relatively dry and mild. Philadelphia in the northeast has hot, humid summers and cold winters, and St. Louis in the central part of the country has hot summers and cold winters. Now, before we get into it, I need to clarify the scope and intent of what we're trying to accomplish with this particular analysis. First, this study was limited to modeling only HVAC-related strategies. We did not model any building envelope improvements, lighting or plug load reductions, or cross-cutting strategies like shading or daylighting.
And Matt, let me comment on that. As I mentioned earlier, we strongly recommend that these load reduction strategies are investigated, whether a project is seeking LEED certification or not. And while the goal of LEED is certainly to use an integrated design approach, we know there are lots of LEED projects where the building envelope and orientation are set, and the engineer is tasked with getting EA Credit 1 points without being able to change these other elements. In one project we know of, the owner decided they wanted LEED certification halfway through the design process, when the building layout and envelope had already been designed. So to help with those types of situations, we decided for this broadcast, our analysis would focus on only HVAC-related strategies. The other non-HVAC strategies would certainly help achieve even larger savings. All right, I'll be quiet now and let you finish.
Secondly, while there are many potential HVAC system types, this study was limited to 5 systems that are the most commonly used for this type of building in the U.S. marketplace today. For example, small package rooftop units, probably the most common system in the U.S., would not likely be used in a multi-story office building. Finally, the target goal for this study was to achieve 2 EA Credit 1 points for each system type. While more points could likely be achieved with the use of additional energy-saving strategies, the goal of this study was to demonstrate which strategies were needed to achieve the minimum 2 points. All right, let's get into the results, starting with rooftop VAV systems. A rooftop VAV system uses a large package rooftop unit to deliver conditioned air to VAV terminals that are located in the ceiling plenum above or near each zone. This system is different than small package rooftop units, which I mentioned would not likely be used in a multi-story office building. For each of the 5 HVAC system types, we'll display a chart like this, showing the resulting energy cost savings for each of the 4 locations. The orange column on the left is the Appendix G baseline building for each location. The corresponding green column on the right is the proposed building. Remember, Appendix G requires the baseline building to use a chilled water VAV system for our example, so the green column depicts the system type we're currently analyzing with several energy-saving strategies that the baseline does not have. The y-axis is overall building energy cost, shown as a percentage of the baseline building energy cost. For example, the proposed building equipped with a rooftop VAV system achieved 15% energy cost savings in Houston compared to the baseline building for that climate zone. That same building, when located in Los Angeles, achieved 3% savings compared to its baseline. In Philadelphia, the savings was 24%, and in St. Louis, about 25%. By the way, the red dashed line is the 14% threshold needed to achieve the minimum requirement of 2 points. Accompanying each chart will be a table like this one. This table indicates which energy-saving strategies were used to achieve the results shown in the previous chart. As we saw, the proposed building in St. Louis achieved about 25% energy cost savings. To accomplish this, the rooftop VAV system used a high-efficiency rooftop unit, 9.7 EER compared to the 9.0 minimum efficiency required by 90.1. Then, the system employed ventilation optimization and improved supply air temperature reset control sequences. John will explain these in a minute. Parallel fan-powered VAV terminals were used in the perimeter zones, and the rooftop units included airside economizers. More savings could likely be achieved in St. Louis with the use of additional energy-saving strategies. For example, cold air distribution could also save energy, but for our example, this strategy was not needed in St. Louis to reach the minimum 14% threshold. For Philadelphia, the same set of strategies was used to achieve 24% energy cost savings. For both Houston and Los Angeles, the system was designed for cold air distribution, 52 degrees supply air compared to the conventional 55 degrees. In Houston, this was needed in order to get beyond the minimum threshold of 14% with a rooftop VAV system. But you probably noticed on the chart that even with cold air distribution, the proposed building in Los Angeles did not reach that minimum threshold. Does this mean that rooftop VAV systems can't be used on LEED projects in LA? No, we wouldn't say that. But it does help emphasize a point we made earlier. I'll show you what I mean. This chart shows the breakdown of energy cost for the baseline building in each of the 4 locations. Since we're using the same building with the same lighting power densities and operating schedules, the amount of energy used for lighting is the same in all locations. But the amount of energy used for HVAC varies by climate. Compared to the other 3 locations in the study, Los Angeles is a fairly temperate climate. It's dry most of the year, and while it does get hot, it doesn't have a lot of hours when it's very hot or very cold. In fact, for a lot of hours, airside economizing provides all or part of the needed cooling. On the other hand, Houston has a lot more hours of hot and humid weather, and both Philadelphia and St. Louis have a significant amount of both hot, humid, and cold weather. Therefore, the total amount of energy used to cool and heat this example building is not as large in Los Angeles as it is for the other locations. To finish the chart, LEED requires plug loads to account for 25% of each location's baseline building energy cost. From this chart, we can see that the total energy cost for the building varies by climate, as we would expect. Now, overlay the percentages. Because lighting energy is the same and the plug loads are required to be 25% of the total, the percentage of building energy cost that is attributable to HVAC is much lower in LA, only 31% of the total compared to 50 or 60% in other locations. Since for this broadcast we're limited our study to only HVAC-related strategies, it's more difficult to achieve a large percentage savings when the only piece that you can impact is smaller.
Okay, let me see if I can play this back. In order to achieve the minimum 2 EA Credit 1 points, the total building energy cost must be 14% less than the baseline building. And since we limited ourselves to get that savings from the HVAC systems only, the amount of energy used by lighting and plug loads doesn't change. So to reduce overall building energy cost by 14% in Los Angeles, for this example, HVAC energy would need to be reduced by nearly 50%. That's a tall order if you can't change the building envelope or lighting. So we'd say that rooftop VAV systems can be used on LEED projects in any of these locations. It's just that in climates like Los Angeles, improvements to the building envelope, more efficient lighting, or cross-cutting strategies like shading or daylighting are that much more important. Okay, as Matt explained, the table lists the energy-saving strategies that were employed for the rooftop VAV system. Let's highlight a few of them. All 4 locations employed ventilation optimization and supplier temperature reset. So let's get a better understanding of those 2 strategies. In a typical rooftop VAV system, the rooftop unit delivers a mixture of outdoor air and recirculated air to several individually controlled zones. ASHRAE Standard 62.1 permits the dynamic reset of outdoor airflow as operating conditions change. The goal of this strategy is to bring in only the minimum amount of outdoor air needed for the current operating condition, thus saving energy. The ventilation optimization strategy combines several demand control ventilation technologies at the zone level with ventilation reset at the system level. Carbon dioxide sensors are installed only in those zones that are densely occupied and experience widely varying population. In this example, CO2 sensors are installed in the conference room and the lounge. These are the best candidates for CO2 sensors since they provide the biggest bang for the buck. However, zones that are less densely occupied or have a population that varies only a little are probably better suited for occupancy sensors. In this example, each of the private offices has an occupancy sensor to indicate when it's unoccupied. This then lowers the ventilation requirement for that zone. Finally, zones that are sparsely populated or have predictable occupancy patterns may be best controlled using a time-of-day schedule in the building automation system. This schedule can either indicate when the zone would be normally occupied or can be used to vary zone ventilation based on anticipated population. These various demand control ventilation technologies are used to reset the ventilation requirement for the respective zones at any given time. This zone level control is then tied together using ventilation reset at the system level. In addition to resetting the zone's ventilation requirement, each VAV controller continuously monitors primary airflow being delivered to the zone. Then, the building automation system periodically gathers this data from all the VAV terminals and solves the equations defined in ASHRAE 62 to determine how much outdoor air must be brought in at the rooftop unit to satisfy all the zones served. Finally, the BAS sends this newly calculated outdoor airflow set point to the rooftop unit, which modulates a flow measuring outdoor air damper to maintain this new set point. Combining demand control ventilation at the zone level with ventilation reset at the system level assures that each zone receives the proper amount of ventilation while saving energy by avoiding overventilation. In a VAV system, it's tempting to raise the supplier temperature at part load conditions in an attempt to save energy. But it's important to understand the trade-offs of this strategy. increasing the supplier temperature can reduce compressor energy and increases the benefit of an air side economizer. For those zones with very low cooling loads, where supply airflow has been reduced to the minimum setting of the VAV box, raising the supplier temperature also decreases the use of reheat energy. However, because the supplier is warmer, those zones that require cooling will need more air to offset the cooling load. This increases supply fan energy. And in non-arid climates, warmer supply air means less dehumidification at the coil and higher humidity levels in the zones. When used, this reset strategy should be designed to minimize overall system energy use. This requires considering the trade-off between compressor, reheat, and fan energy, while not forgetting the impact on space humidity. These competing issues are often best balanced by first reducing supply airflow, taking advantage of the significant energy savings from unloading the fan. Then, after fan airflow has been reduced, raise the supplier temperature to enhance the benefit of the air side economizer and minimize reheat energy. This slide shows an example of a simple supplier reset strategy that is based on outdoor temperature. When the outdoor dry bulb temperature is warmer than 70 degrees, no reset takes place, and the supplier set point remains at its design value of 55 degrees. At temperatures above 70, the outdoor air provides little or no cooling benefit for economizing, and the cooling load in most zones is likely high enough that reheat is not yet activated. Additionally, the colder supplier temperature allows the system to provide sufficiently dry air to the zones, improving part load dehumidification. Then, when the outdoor dry bulb temperature is between 60 and 70 degrees, the supply air temperature set point begins to reset upward. In this range, reset enhances the benefit of the economizer, and any zone level reheat energy is reduced. Finally, when the outdoor temperature is colder than 60 degrees, no further reset occurs and the supplier set point remains at 60. Limiting the amount of reset allows the system to satisfy cooling loads in interior zones without needing to substantially oversize VAV terminal units and ductwork. Okay, let's move on to our next system type, self-contained VAV.
Sure, John. In many ways, a self-contained VAV system is similar to rooftop VAV, except that the packaged DX units are located indoors, typically in a small mechanical room on each floor of the building. Also, they contain water-cooled condensers, which are piped to a cooling tower. Here's the chart comparing the proposed building with a self-contained VAV system to the same baseline building, which, as you recall, has a chilled water VAV system. The proposed building achieved 7% energy cost savings in Houston, about 4% in Los Angeles, 15% in Philadelphia, and about 16% in St. Louis. Since the air side of this system is very similar to rooftop VAV, several of the energy saving strategies are the same. Like before, the ventilation optimization and improved supply air temperature reset control sequences were used in all 4 locations, and parallel fan-powered VAV terminals were used for the perimeter zones. For both Houston and Los Angeles, the system was designed for cold air distribution, 50-degree supply air in this case. Some of the differences stem from the fact that this system includes a condenser water loop. First, the condenser water system was designed for a lower flow rate, 2.5 GPM per ton, versus the past conventional practice of 3 GPM per ton, and the self-contained units were equipped with water-side economizer coils, which use the cool condenser water for pre-cooling when conditions permit. Finally, a total energy wheel was used to precondition the entering outdoor air for the proposed building in Houston. This strategy not only saves energy, but also allows for a significant reduction in equipment cooling capacity.
So Matt, with this system, the proposed building didn't reach the minimum 14% threshold in either Los Angeles or Houston.
That's right, John. Well, for LA, most of the systems will be facing this challenge we discussed earlier. Since HVAC only accounts for 31% of the total energy cost, big gains need to be made when we limit ourselves to get that savings from the HVAC systems only. Plus, self-contained units are typically not equipped with airside economizers. LA is a prime climate for airside economizing, and the baseline chilled water VAV system includes an economizer. so the proposed building started out in the hole and had a lot of ground to make up. Houston, on the other hand, has a lot of cooling hours. Water-cooled self-contained equipment typically uses scroll compressors, which are less efficient than the water-cooled centrifugal chillers that are the baseline for the building of this size. So for this example, the proposed building also starts in the hole due to the difference in efficiency between the cooling technologies. Plus, Houston is a humid climate, so the savings from the water-side economizer is not as impressive as it is in the other locations.
As we mentioned earlier, this does not mean that a self-contained VAV system cannot be used on LEED projects in these two locations. It just means that improvements to the building envelope, more efficient lighting, shading, or daylighting are more likely needed. And remember, our example is a fairly large building, so the baseline system is chill water VAV with water-cooled centrifugal chillers. For smaller buildings, the baseline system will be different, so the results will vary. Okay, back to the strategies implemented for this system type. We talked about a few of them already, so let's dig into some of the others. Heat generated by light fixtures warms the air in the ceiling plenum. Fan-powered VAV boxes use this warm air from the plenum as a form of heat recovery. In a parallel fan-powered VAV box, primary airflow is reduced as the cooling load decreases. When the box reaches its minimum airflow setting, the small fan activates to draw warm air from the ceiling plenum and mix it with cool primary air. If more heat is required, the heating coil can be activated. Parallel fan-powered VAV boxes can save energy because they use warm air from the ceiling as the first stage of heating. This delays the need to use new energy by activating the heating coil. As we mentioned, these self-contained units are typically not equipped with air-side economizers. They are usually installed in small mechanic rooms that are located in the core area of each floor of the building. Ventilation air is ducted down a vertical shaft to each floor, but that duct is usually sized for only the minimum ventilation requirement, not full economizing airflow. But this type of equipment can include a water-side economizer coil. When the weather and heat rejection load are such that the cooling tower is able to make cooler water, a valve diverts this cool water through the economizer coil that's located upstream of the evaporator. This cool condenser water is used to pre-cool the entering air, reducing the cooling demand on the refrigeration system and saving energy. All right, what's next?
The next system type is a chilled water fan coil system. Chilled water and hot water are produced at a central location and pumped throughout the building to individual fan coil units that are installed in or near each zone. A dedicated outdoor air system is used to condition all of the ventilation air and then divert it either directly to each zone or to each fan coil unit. Here's the chart comparing the proposed building with a chilled water fan coil system to the baseline building. The proposed building achieved 18% savings in Houston, 14% in Los Angeles, 21% in Philadelphia, and 22% in St. Louis. Since this is a water-based system, all 4 locations use strategies targeted at the chilled water system. Both the chilled water and condenser water systems used low-flow designs, 1.7 GPM per ton on the chilled water side and 2 GPM per ton on the condenser water side. And a high-efficiency water-cooled centrifugal chiller was used at 0.59 kW per ton. Now, at first glance, this probably doesn't sound like high efficiency, but remember, the chiller is operating at different temperatures and lower flow rates than standard ARI conditions. For comparison, ASHRAE 90.1 would require a minimum efficiency of 0.69 kW per ton at these design conditions, so this chiller is actually 15% more efficient. On the air side, the fan coils are equipped with multi-speed rather than single-speed fans. This allows the controller to reduce fan speed at part load, saving fan energy. This strategy has the added benefits of improving dehumidification and reducing sound levels at part load. The next 2 strategies relate to the dedicated outdoor air system. The conditioned outdoor air is delivered cold rather than neutral directly to the spaces. And for 3 of the locations, a total energy wheel is used to precondition the entering outdoor air. For the other location, Los Angeles, the dedicated outdoor air system had to be designed for demand control ventilation in order to reach the minimum threshold. A dedicated outdoor air system is typically designed to deliver only minimum ventilation, not full economizing airflow. So a plate and frame heat exchanger was added to the chiller plant for Los Angeles, Philadelphia, and St. Louis to provide waterside economizing. Lastly, a chiller tower optimization control sequence was used. This strategy uses the chiller plant control software to determine the optimum condenser water temperature set point that minimizes the combined energy use of the chiller and cooling tower.
Since this is the first of our systems to use a dedicated outdoor air system, let's get a better understanding of the strategies related to that. A dedicated outdoor air system devotes one air handler to condition all the incoming outdoor air used for ventilation. Meanwhile, the local fan coil unit handles the sensible load in each zone. The conditioned outdoor air is typically delivered to the zone in one of two ways. The first approach is to duct the outdoor air directly to the intake of each fan coil, where it mixes with return air from the zone. Then the fan coil maintains space temperature by cooling or heating this mixture. The second approach is to duct the conditioned outdoor air directly to each zone, as shown in this slide. In this configuration, the fan coil cools or heats only the recirculated air to maintain space temperature. A variation of this second approach is to duct the outdoor air to the supply side of each fan coil, where it mixes with supply air before being delivered to the zone. Again, the fan in each local unit only needs to move the recirculated air, rather than the mixture of outdoor and recirculated air. When the conditioned outdoor air is delivered directly to the zone at a cold temperature, rather than reheated to neutral, this cold air offsets some of the space-sensible cooling load, allowing the local fan coils to be smaller and use less energy. When a chill water or refrigerant coil is used to dehumidify the outdoor air, a byproduct of that dehumidification process is sensible cooling. The dry bulb temperature of the air leaving the coil is colder than the space. If the conditioned outdoor air is delivered at this cold temperature, rather than reheated to neutral, this cold air offsets some of the space-sensible cooling load. This allows the local fan coils to be smaller and use less energy. Plus, you avoid any energy used to reheat the air in the dedicated outdoor air unit. On the other hand, if this dehumidified air is then reheated to neutral, some of the sensible cooling performed by the dedicated outdoor unit is wasted, and that cooling must be done by the fan coils. Now, I talked about this topic in detail on last September's broadcast on dehumidification. So if you want more on this subject, you may want to view that broadcast. Now, because all the outdoor air is brought in at a central location, including an air-to-air energy recovery device, to precondition the outdoor air becomes more feasible. When it's hot and humid outside, a total energy wheel transfers sensible heat and moisture from the outdoor air to the cooler, drier exhaust airstream. This pre-cools and pre-dries the entering outdoor air, saving cooling energy. When it's cold outside, the wheel transfers sensible heat from the warmer exhaust air and uses it to preheat the entering outdoor air. This saves heating energy. A side benefit is that the total energy wheel also transfers moisture from the exhaust air to humidify the dry air entering from outdoors. This can save energy if humidification equipment is being used. In hot or cold climates, total energy recovery typically results in greater potential for equipment downsizing and more energy savings than sensible recovery devices.
Okay, next up is the water source heat pump system. In a conventional system, all the heat pumps are connected to a common water loop, along with a cooling tower and hot water boiler. Like in the fan coil system, a dedicated outdoor air system is used to condition all the ventilation air. Here's the chart comparing the proposed building with a water source heat pump system to the baseline building. The proposed building achieved 15% savings in Houston, 8% in Los Angeles, 17% in Philadelphia, and 19% in St. Louis. This system has some inherent energy advantages. At times during the year, some heat pumps in the building may operate in the cooling mode, while others simultaneously operate in the heating mode. The heat rejected to the water loop by the heat pumps that are cooling helps keep the temperature of the loop warm enough to provide heat for those heat pumps that are in heating. This is a form of heat recovery during these times. Both the cooling tower, and the boiler can be shut off, saving energy. For each of the 4 locations, high-efficiency heat pumps were used. Also, a loop temperature optimization control sequence was employed. More on that in a moment. Similar to the fan coil system, the conditioned outdoor air is delivered cold rather than neutral directly to the space. As John mentioned, this can allow the heat pumps to be downsized and save energy. And if the outdoor air is delivered directly to each space, the fan inside the heat pump does not need to operate in order to ventilate the space. This affords the opportunity to cycle that local fan on and off along with the compressor, saving fan energy at part load conditions. This strategy was used for the proposed building in Los Angeles. Next, for 3 of the locations, a total energy wheel was used to precondition the entering outdoor air. And finally, for LA, a waterside economizer was used on the heat pumps. The configuration is similar to the self-contained units, as the waterside economizer coil is mounted at the inlet of the heat pump. When the temperature of the water loop is cool enough, this coil can be used to pre-cool the air and save compressor energy.
Let's review the loop temperature optimization strategy since it's unique to water source heat pump systems. A system-level controller is used to operate the pumps and coordinate cooling tower and boiler operation. To maximize the energy-related benefits of this system, the loop water temperature is allowed to float over a wide range, for example, between 60 and 90 degrees. In the cooling mode, the compressor in a water source heat pump is more efficient if the entering water temperature is cooler. However, making that cooler water often requires the cooling tower to use more energy. The loop temperature optimization strategy uses the system-level controller to reset the loop temperature set point in an attempt to minimize the combined energy consumed by the heat pumps and cooling tower under the current operating conditions. Now, while it was not part of this study, a well-known variation of this system is the ground source heat pump system. Ground source systems do not actually get rid of the heat, they store it in the ground for use at a different time. During the summer, the heat pumps extract heat from the building and transfer it to the ground. When the building requires heating, this stored heat can be recaptured from the ground. In a perfectly balanced system, the amount of heat stored over a given period of time would equal the amount of heat retrieved. Ground source heat pump systems offer the potential for saving energy because they can reduce or eliminate the energy needed to operate a cooling tower and/or boiler.
Our last comparison takes the chilled water VAV system defined by Appendix G of 90.1 for this baseline building and modifies it to improve its energy performance. Chilled water and hot water are produced at a central location and pumped throughout the building to VAV air handlers. Each air handler delivers a mixture of outdoor and recirculated air to several VAV terminals which serve the individually controlled zones. Here's the chart comparing the proposed building with the high-performance chilled water VAV system to the baseline. The proposed building achieved 19% savings in Houston, 14% in LA, 25% in Philadelphia, and 26% in St. Louis. Since this is the last system we're discussing, you've seen most of these strategies already. Similar to the fan coil system, low-flow designs are used for both the chilled water and condenser water systems, along with a high-efficiency water-cooled centrifugal chiller and the chiller tower optimization control strategy. You may have heard Trane refer to this concept as an earthwise design for chiller plants. The VAV air site strategies are similar to the Rooftop VAV system. The same ventilation, optimization, and supply air temperature reset sequences were used for all 4 locations. And parallel fan-powered VAV terminals were used in 3 of the locations. For Los Angeles, Philadelphia, and St. Louis, the system was designed for cold air distribution with 48-degree supply air. Since air handlers typically have more fan choices available, a high-efficiency airfoil supply fan was used.
Well, we didn't talk much about the chiller plant back in the fan coil system, so let's cover the strategies related to that part of the system now. Traditionally, the performance of a chilled water system focused on the chiller because it was the largest energy consumer in the plant. 30 years ago, the chiller accounted for about 70% of the annual energy used by the chiller plant, while the pumps and cooling towers accounted for the remaining 30%. However, manufacturers of chillers have made and continue to make great progress in improving chiller efficiency. So much so that today pumps and cooling towers make up nearly half of the plant's annual energy use. So while using a high efficiency chiller still has a significant impact, this shift has created more opportunities to reduce overall plant energy use by examining the interaction between pumps, towers, and chillers. One such opportunity is the selection of design flow rates for both the chill water and condenser water sides of the system. This slide shows an example 450-ton chill water plant using conventional flow rates of 2.4 GPM per ton on the chill water side and 3 GPM per ton on the condenser side. The table shows the kW draw of the chiller compared to the pumps and cooling tower fans. Now see what happens when the same system is designed for lower flow rates. Consistent with the recommendations of the ASHRAE Green Guide, the flow rates are reduced to 1.5 GPM per ton on the chill water side and 2 GPM per ton on the condenser side. The chiller consumes more power, but look at the drastic reduction in pump and tower energy. These reductions more than offset the increase in chiller power. In fact, the full load power draw of the overall plant is reduced by 4%, and the savings can be even larger at part load conditions. Now earlier for the self-contained VAV system, I described a water-side economizer coil that was used to pre-cool the air. Another configuration of a water-side economizer is to use a plate and frame heat exchanger to pre-cool the water that is returning to the chiller plant. In this configuration, the heat exchanger is also connected to the condenser water system. When conditions allow and the cooling tower is able to make cold enough water, this cool condenser water is used to pre-cool the water returning from the air handlers, reducing the cooling demand of the chillers and saving energy. This type of economizing strategy was used in the fan coil system also, where the dedicated outdoor air system was sized to provide only minimum ventilation. In that case, airside economizing is probably not feasible. The last strategy related to the chiller plant was the chiller tower optimization control sequence. The chiller and cooling tower react differently to changes in the condenser water loop. If the temperature of the water entering the condenser increases, the chiller consumes more power. But the cooling tower uses less power because it's easier to make warmer water. On the other hand, if the water temperature decreases, the chiller's work is easier and it uses less power. But the cooling tower needs to work harder to make the colder water. The question is, what's the impact on the combined energy of the chiller plus tower fans? And what is the temperature that results in the lowest combined energy use? The answer is, it depends. And this optimum temperature changes as conditions change. The chiller tower optimization strategy uses the chiller plant control software to determine this optimum condenser water temperature set point at any given time to minimize the combined energy use of the chiller and cooling tower. Now for 3 of the systems we discussed today, cold air distribution was used in some of the locations. The appeal of cold air lies in the corresponding reduction in supply airflow. This can significantly reduce fan energy use and can also result in smaller fans, air handlers, ductwork, and VAV terminals. But supplying air at a colder temperature can increase reheat energy and result in fewer hours when the airside economizer can provide all the necessary cooling. These impacts partially offset the fan energy savings. Therefore, intelligent system control, such as the proper use of supplier temperature reset, is crucial to fully realize the potential energy savings of a cold air VAV system. In addition, this strategy lets you balance energy cost savings with first cost savings. Downsizing the ductwork saves first cost, but results in less fan energy savings than if you kept the same size duct. So it warrants an analysis to best achieve the goals of your specific project. Well, Matt, I know this trace study was a lot of work for you and your team, so thanks. But before we move on, let's review our purpose for sharing this study. For those of you who are less familiar with the process for achieving LEED EA Credit 1 points, The results from this example analysis cannot be submitted for your specific LEED project. The USGBC requires the actual building to be modeled in order to document the projected energy savings.
That's right, John. Our hope is that the results from this example study will provide some guidance as to what energy saving strategies should be investigated for the particular HVAC system that you may be leaning toward using on a given project. Maybe this will give you a starting point to determine which strategies should be modeled. I also want to point out that the results of this study are also published in the Engineers Newsletter that accompanies this broadcast. If you did not get a copy today, ask your local coordinator or visit the Trane website. And for Trace users, the Trace User's Manual includes step-by-step instructions for modeling most of these strategies in that software.
Be careful not to discard any of the system choices investigated in this study just because it didn't achieve at least 14% energy cost savings in this particular example. Actual savings depends on the layout and usage of the specific building, the climate, and the baseline system requirements. Remember, our example was a fairly large building, so the baseline was equipped with a chill water VAV system. For smaller buildings, the baseline system will be different. As Matt mentioned, the purpose of this study was to help identify which strategies you might want to investigate for the particular HVAC system you're leaning toward using on a given project. It's not a comparison of one system type to another. That's a separate exercise, which is much more dependent on the specific characteristics and constraints of the project. Plus, when comparing the different system types for a given project, installed cost becomes a critical variable. Finally, there are many other energy saving strategies that were not included in this particular study. I mentioned geothermal earlier, and ice storage is another strategy that can help reduce overall building energy cost. In fact, last year, we published an Engineers Newsletter that included an example analysis of using ice storage to achieve LEED EA Credit 1 points. If you've not read it, you can download it from the Trane website. And ice storage complements some of the other strategies we discussed, such as low temperature air and water systems. Any of these systems can be used on a LEED project. It's just that in some situations, load reduction strategies through envelope and lighting may be needed to reach the 14% minimum threshold. And these strategies should be investigated anyway. Another way to look at it is this. If the minimum 14% savings has already been achieved through load reduction strategies, all of these systems can deliver additional energy cost savings to achieve more EA Credit 1 points.
Earlier, we referred to the Energy Policy Act of 2005. Remember that in order to claim the $1.80 tax deduction for fully qualifying property, the IRS requires that the energy savings be proven through the use of a qualified software tool. The requirements of this compliance process are very similar to the requirements defined by LEED and Appendix G of ASHRAE 90.1 with some minor modifications. So, if a project already involves computer modeling for LEED certification, it wouldn't require much additional work to document the expected energy savings for this tax deduction. Reaching the 50% energy and power cost savings marks will likely be difficult for many buildings, but keep in mind that partially qualifying tax deductions are also available for the envelope, lighting, service water heating, and HVAC systems. A building achieving 16 2/3% cost savings in any of these categories when compared to the standard 90.1 2001 reference building qualifies for a tax deduction of up to 60 cents per square foot. It's interesting to note regarding the interim lighting rule that buildings that already comply with the building area lighting power density requirements for LEED NC 2.2 are likely to already qualify for deductions because of the stricter limits set by standard 90.1 2004.
As John mentioned, for these analyses, we limited the scope to only HVAC-related strategies. We did not model any building envelope improvements, lighting or plug load improvements, or cross-cutting strategies like shading or daylighting. But we know that these other strategies can have a significant impact on energy use. So we've asked Neil Maldives to join us to emphasize that fact. Neil?
Thanks, Jeannie. More efficient lighting better glass, shading of glass, and building orientation will all help reduce the building load and therefore impact energy consumption. In addition, there are other energy-consuming processes in the building that can be improved to save energy. During this next segment, I want to paint the big picture of building energy use and demonstrate just how important these other areas are. Even though mechanical and electrical engineers are not typically involved with decisions around the building envelope, be aware that these decisions can have a significant impact on the energy performance of the overall building. Architects are much more in touch with these factors than in the past, but challenging their decisions and expressing your concern over their impact rather than accepting these decisions may help the design team deliver a better project to the owner. Keep in mind, many LEED points can be acquired at this stage. Here is an example of a cooling load for a typical office building in the southwestern part of the U.S. For those of you located in other regions of the country or the world, your buildings will differ depending on your climate and the type of construction specifics. The purpose of this example is just to show for our discussion that the building envelope and other internal loads can contribute to a large percentage of the building load. Looking at the data, we see that 23% of the entire cooling load has been created by the solar load through the windows. You might be thinking, where did this data come from? The simple answer is from modeling the building. Most modeling tools have excellent reporting capabilities that give engineers a large amount of information pertaining to the building modeled. Understanding and using this information can give you the opportunity to lead a discussion with the rest of the building design team and possibly recommend to the architect other window glazing or shading options be considered. This is a great opportunity for the engineer to expand their value to the design team by modeling and analyzing various options early in the design process so you can help the team make the right choices for the client. In a few minutes, I'll go through some examples of how modeling helped us discover real savings for some building owners. Windows are a typical place to start, and as we will see, can have a huge impact on the energy performance of a building. Windows are commonly described according to the number of panes of glass and whether any type of tint or coating has been applied to the glass to alter its performance. High-performance windows include heat-absorbing, reflective, and spectrally selective glazing. When selecting a glazing option, the design team should choose one that maximizes daylighting and occupant comfort, minimizes energy use and glare, and still meets the project's design and aesthetic criteria. As this chart shows, glazing options are available that meet a wide range of performance criteria. What kind of impact do windows have on energy use? Looking at our example office building, we see that the different window types result in significant differences in energy performance for different types of windows used. If this is an existing building with older single-pane windows, replacing the windows with higher performing glazing can reduce energy use by 5 to 25%. A new building wouldn't see as much savings because of the minimum requirements in Energy Code and ASHRAE 90.1. In this case, of course, the savings from using higher performance glazing options is not as dramatic, but can still be significant. Changes to window glazing are easily modeled to see the impact on energy performance for a building. Work with the project's architect to define suitable options to model, and you can show the design team the effects of the energy performance from the choices made. Looking at the same office building in the Southwest, notice how insulation and roof color can also have a significant impact on the energy cost of a building. Simply adding insulation and choosing a lighter shade for the roof can reduce energy use. Again, using our office building example, we see that adding additional insulation and choosing a lighter color going up to R30 reduces costs more than 30% over a typical black roof with R19 insulation. As we saw in the previous example, window glazing options, roof insulation, and roof color can all have a significant impact on energy performance. Of course, depending on the specifics of the project, there are other aspects of the building envelope to consider that will also have an impact on the building energy performance. The orientation of a building often is fixed due to site constraints. However, for those sites where there is a choice, analyzing the effect of orientation on energy and equipment costs can lead to a more energy efficient building. While it is important to look at each project on an individual basis, as a general guide, long, narrow buildings facing south with their long axis running east-west will have lower peak cooling loads and electricity demand costs. Conversely, buildings facing east or west with their long axis running north-south will have higher peak cooling loads and electricity demand costs. Daylighting through perimeter windows or skylights and other types of architectural glazing features can improve natural lighting and creating a pleasant working atmosphere. Daylighting strategies may be particularly effective using skylights in large open areas such as warehouses and manufacturing plants, and in office spaces where the electrical lighting system output can be efficiently varied over a wide range of light levels. Well-designed landscaping can reduce cooling costs from summer heat gains in the building. Trees planted on the east, west, and south sides of a building can effectively reduce summer solar heat gains through windows. Trees can even produce a natural cooling effect in the areas surrounding a building by evaporating water through their leaves. This also can help offset the heat island effect found in many urban areas. While trees and landscaping can't be used in the calculation of LEED EA Credit 1 points, if properly used, they can help save energy, and that's what it's all about. Matt?
As we discussed earlier, these ideas should be considered whether you are designing for LEED or not. By looking at the other building elements and systems that impact energy use, you can improve the energy performance and gain more LEED points.
Right. As we saw here, HVAC improvements aren't the only building systems that can contribute to this improvement. The building envelope and internal loads, such as lighting, can have a significant impact on improving energy performance. Modeling of the building will be required to determine what the expected energy cost savings for the overall improved building. But the effort put into modeling high-performance building options can yield a significant reduction in energy use. The ASHRAE Green Guide, the Advanced Energy Design Guide series, and even the standard 90.1 User's Manual are great resources of information that offers approaches and suggestions on how you can modify your design to improve energy performance. Let's move on and consider the next group of items that also have a significant impact on energy use in a building. Outside of having designed the right HVAC system for your building, how the building is ultimately used and what types of equipment go into the building have the greatest impact on overall energy use. Don't stop with just the building design. Operational factors have a large impact on your energy consumption, whether your building is new or has been around for decades. Operating schedules cannot get you LEED credit, but are a huge opportunity to save energy in real life. In retrofit work, we have historically found more savings through proper scheduling than in any other energy savings areas. Proper scheduling for HVAC lighting and other energy-consuming equipment in the building is key. Matching system ventilation to the actual occupancy pattern of the building is another energy-saving area. Recall John's discussion on the ventilation reset earlier in the broadcast. Often we find building systems operating to maintain temperature or provide ventilation for areas of the building that are long since occupied. Often, this is because the outdated original design criteria no longer exists. Beyond proper scheduling, having an HVAC system that can automatically respond to the varied occupancy can have a huge impact on the energy bill. The impact of energy consumed by office equipment has grown substantially over the last few decades and can be a significant amount of the energy use in a building today. Consider some of the tools, products available that can manage the energy consumption when idle. 20 to 50% savings on your office equipment energy use is typically achievable when using strategies applied building-wide. For example, a computer monitor can be equipped with a workstation occupancy sensor that automatically shuts it off when it senses no one is sitting at the workstation. As this chart demonstrates, this can save $54 per monitor versus leaving it on all the time. We have found energy savings opportunities in all types of ages, and buildings. In fact, some of the newest buildings can be the worst offenders. Decisions made in the spirit of value engineering were made that can completely change the energy performance of the building. Installation issues also create savings opportunities. Incorrectly installed equipment or changes to the system design made in the field can create inefficient operating conditions that impact energy use.
The good news is lately, there's been a stronger focus from customers and owners on green design and LEED. Large organizations are also implementing more corporate green and sustainable initiatives. With new emphasis by customers on having better energy performance, this gives engineers the opportunity to explore, analyze, and recommend energy-saving designs that would not have been considered just a few years ago. Neil, we've also seen an increased interest in commissioning, right?
That's right, Jeannie. You should consider commissioning for all of your projects. Our experience has shown that most operational issues could have been avoided if the HVAC and control systems were commissioned. Commissioning is the only way to ensure the systems are operating per your design, and studies have shown the additional cost to perform commissioning is far offset by the cost saved to fix problems later and the potential energy savings lost due to poor operation. It's also a prerequisite if your customer is considering LEED certification, and you can also get an extra point for additional commissioning activities. We've also mentioned the importance of modeling several times. Use modeling to help make decisions about design elements that will have an impact on building energy use. Once you've created your base model, it's easy to create alternatives to see how different design choices may impact building energy performance. Modeling takes into account the interdependencies of all the building systems and gives the most accurate way to look at changing design elements to see what impact that specific change will make on the overall building. The time and effort spent is well worth it, as you can use this process to determine what are the best options for the building. We have successfully used the modeling process to predict savings on our performance-based contracts, and we're getting more requests from our field offices and customers for assistance with modeling energy alternatives to help in making decisions. Here are some examples of projects where we have made a significant improvement in energy performance by addressing the building as a whole and not just focusing on HVAC systems. The first example shows the results for several buildings at a college campus on the East Coast. The saving strategies implemented were the same for all of the individual buildings, and this is the total result. Lighting had been partially addressed at the campus, but we still found many areas that were not addressed. Also, we installed occupancy sensors that contributed to the savings. With the automation system, we addressed scheduling and thermostat control in the facility. Remember, I mentioned earlier that we often achieve significant energy savings just through proper scheduling and setback of temperatures. This facility was built in the 50s and had a constant volume system that had simultaneous heating and cooling. We modeled the facility with a VAV system and were able to show significant energy savings. The chiller and boiler, which can consume most of the energy for this project, actually turned out to still have savings, but not be as much as one would expect. Lastly, we recommended a local power monitor for all the desktop computers, which monitored the idle time of the computer and shut it down along with any task light that may be at the desk. Next, we have an example of savings for a hospital complex in the Southeast. Again, we see substantial savings came from doing a lighting retrofit throughout the hospital. The hospital had a fairly new building automation system, but was not using it to its full potential. We worked with the hospital staff and created new schedules and setback temperatures in the administrative areas that brought big savings. Installing water-saving devices, though not energy-related, can also generate water and sewer bill savings. And water conservation can help achieve points towards LEED certification. In our last example, we have a comprehensive project that was done for a mid-sized school district in the Northeast. Faced with very old buildings, the school district was interested in modernizing the buildings as much as possible. We touched nearly all of the building systems and generated savings from them, as you can see in the chart. The total savings for the school district was 40% over their previous year's utility costs. Independently, none of the saving strategies in these projects are all that dramatic or exciting, but by careful analyzing the savings potential and careful execution, the overall result, as the previous examples show, can have a significant impact on energy performance. We used our modeling process on all of these projects to determine the savings which was to be guaranteed under a performance contract. Currently, we have an excellent track history with our guarantee projects, and in many cases, we are exceeding the energy saving projections. Consider looking at the bigger picture when considering the energy performance of your building projects in the future. Don't forget, most of the energy improvements you do can also enhance your ability to achieve LEED points. Jeannie?
Thanks, Neil. Trane's CDS team staffs a support center that helps users of the Trace software with issues ranging from how to use the program to how to model specific system configurations or strategies. Last year, the support center responded to over 20,000 phone calls and emails, and they've seen a significant increase in the use of Trace for LEED projects. They also see a lot of the oversights people make when energy modeling. In addition, Neil's team reviews energy modeling results for projects across the country. So together, they see many of the pitfalls. For this last segment, we've asked Matt and Neil to assemble a list of the most common oversights they've seen when working with energy models. We thought that this would be a great opportunity to help you learn from their experience. Matt, would you cover this last section?
Absolutely, Jeannie. Since we're talking about LEED, I'm going to begin by focusing on the performance rating method, as outlined in Appendix G of ASHRAE 90.1. Starting with common oversights made for building envelope, the first is the maximum glass percentage for the baseline building is not necessarily the same as in the energy cost budget method. For the performance rating method, the total area of vertical fenestration should be equal to the total area of glass used for the proposed building. But if the proposed building contains more than 40% glass, the baseline building must be capped at 40%. In addition, Appendix G requires that the glass on the vertical surfaces be evenly distributed in horizontal bands across all orientations of the baseline building. This is often overlooked. Next, Appendix G directs you to model lightweight roof, wall, and floor assemblies in the baseline building. This means basically steel-framed walls and steel joist floors. Many energy modelers just use whatever was modeled in the proposed building. The final common error for the envelope is pretty obscure, but people often forget to set the reflectivity of the roof surface equal to 0.3. Next, I'll cover the common errors made when modeling HVAC systems using the performance rating method. The most common error is incorrectly selecting the appropriate HVAC system type for the baseline. Appendix G includes a set of tables to define which HVAC system to assume for the baseline. For small, low-rise buildings, this is often packaged rooftop air conditioners or heat pumps. For mid-rise buildings, the baseline system is a packaged rooftop VAV system, and for larger or taller buildings, the baseline is VAV with chilled water, as you saw in our previous examples. Another error that is commonly made is not breaking out the component energy rates for HVAC packaged equipment. Energy modeling tools typically account for these components individually rather than combining them. This means that fan, compressor, and condenser energy are all accounted for with separate program entries. Part load equipment performance requirements are also often overlooked in this process. Equipment performance must meet all stated equipment requirements to comply with the standard. Energy modelers often select from pre-constructed equipment libraries and simply override the full load energy rates while neglecting the part load performance. Improperly calculating fan power or forgetting to update it after other modeling changes affect supply airflow is another issue we commonly run across. Since peak fan power is dependent on the supply airflow for each system when using Appendix G, it can not only be tedious when changes are made, but it's easy to overlook correcting the fan sizing when these airflow changes occur. In addition, Appendix G requires that supply and return fans must be capable of cycling to meet heating and cooling loads during unoccupied hours. Another mistake that we frequently notice is modeling peak pumping power for each pump rather than the combined pump energy for either the chilled water or condenser water loop. For instance, modeling a baseline chilled water system requires the combination of both the primary and secondary chilled water pumps not exceed 22 watts per GPM. To ensure proper building control is maintained, Appendix G also restricts the number of unmet hours that can occur in both the proposed and baseline buildings. Either model cannot register more than 300 unmet load hours, and the proposed cannot exceed the baseline building by more than 50 hours to ensure cost savings are not achieved by sacrificing occupant comfort. Because of the complex nature of building simulation, unmet hours can be difficult to eliminate in some cases. However, one of the main causes for unmet load hours is actually related to another commonly overlooked requirement of Appendix G. That is, systems that have more than 10,000 CFM must have controls that allow the system to come on prior to scheduled occupancy to meet the pull-up or pull-down demands of the system. This control is known as optimum start control. Yet another frequent oversight is not using a 20-degree difference between supply air and room air temperature to determine design airflow for the baseline building. This provides designers the ability to optimize energy performance by reducing system airflow or by resetting supply air temperature for the proposed building. The final commonly seen error related to the performance rating method is not using 8760 hours of weather data when simulating the energy use. Unlike the energy cost budget, which only required 1,400 hours of simulation, the performance rating method requires full-year 8760 weather simulation. Now that we've discussed modeling errors that focus exclusively on the performance rating method, let's broaden the subject a bit and discuss some general energy modeling mistakes that we commonly encounter. The first is probably the most flagrant oversight and relates to one of the more tedious aspects of energy modeling. That is, improper modeling of occupancy, lighting, and receptacle schedules. Because of the tedious nature of creating these schedules, users select pre-created or default schedules to save time without verifying that the selected schedules are reasonable estimates for a given thermal zone. Just a 1 or 2 hour discrepancy in any of these schedules from actual building operation can easily result in a reduction or addition of hundreds of HVAC system runtime hours throughout the simulation. Another mistake that can quickly skew a quality energy model is the use of default equipment at standard design conditions when the actual design conditions vary significantly. A good example of this relates to the Los Angeles analysis results you saw earlier. Selecting a tower and chiller at standard ARI conditions for LA-type weather conditions can have a serious impact on the accuracy of the model. This concept also applies to equipment features or options that significantly affect full or part load of performance. Some other frequently identified errors include oversimplifying the model by combining thermally dissimilar zones and incorrectly modeling a system or zone level ventilation. When project deadlines are nearing, sometimes it's easier to force an energy model to meet some expected outcome rather than allowing the tool to properly simulate the results. In many cases, this can result in unintended simulation consequences that are often difficult to identify, such as a reduction in zone temperature or humidity control. Similarly, we often run into simulations where a software tool is used beyond its intended purpose in an attempt to model features that have yet to be incorporated into the tool. Caution must be taken when attempting this because it requires an in-depth understanding of the tool's existing functionality, sound theory behind the workaround, and a means to verify the results are reasonable. The last generally modeling mistake that we will address today is carrying load design assumptions over to energy simulation. For example, if the building model is assumed to be fully occupied during design analysis, and that assumption were to be carried over to the energy simulation, that could drastically impact the model and would likely cause the simulation to be cooling dominated. When it comes to energy modeling, a good software simulation is highly dependent on the accuracy of the information entered, knowledge of the software tool, and the level of industry experience to interpret the results. Jeannie?
Thanks, Matt. That brings us to the question and answer portion of our broadcast. So let's get started. If we don't get to your question on the air, don't worry. We'll answer all questions offline. We've got quite a few here. So John, I'm going to throw the first one to you. As an architect, I often optimize an envelope design for high-performance building to be 20 to 30% better than 90.1. However, when I receive HVAC designs back from the engineer, I see the same square foot per ton loads that I've seen for years. Even using trace, engineers seem to be reluctant to push the envelope when it comes to really sharpening their pencil and optimizing the HVAC system designs. What reasons do you think could be the rationale for this dilemma?
I think if you ask what reasons could be the rationale for the dilemma, I guess a situation I could think of is a challenge for the engineer would be if they designed the HVAC system for that optimized building envelope and orientation and so forth, and then if some elements of that envelope were cut maybe in a budgeting process or a value engineering process, it's possible that the HVAC system wouldn't be sufficient anymore. And so that might be a rationale or one way that might actually happen. Really what I think this does is highlights the need for that teaming approach between the architects and engineers, including the building owner, so that when the architect does take that step of designing an optimized envelope, the HVAC engineer knows that, works together, puts together an optimized HVAC system, and the building owner understands those two are connected, so that if there have to be money cut and something is cut out of a project, that they understand that there's relationships all the way down. So that's what I'd say.
Okay, thanks, John. Next one's going to go to John also, and it is there a way to achieve LEED NC EA Credit 1 using the Advanced Energy Guides for buildings with multiple uses, specifically a single building that contains office space and equipment or vehicle repair shops? You want that one too?
I don't think the LEED rating system or the accompanying reference guide address those mixed-use type buildings and put a limit on that. But I know there was a credit interpretation ruling somewhat recently that dealt with a building that had about a third, I think, of office space and maybe two-thirds of something else, where the USGBC issued a ruling that it could not use the Advanced Energy Design Guide for small offices. So I'm not exactly sure where that limit is. But on top of that, the USGBC does give you some leeway, the project team the leeway to make a case for why they should consider one type of usage or another.
Great, thanks, John. Matt, the next one's going to be for you, and it is, hasn't the tax deduction been extended through 2009?
Well, there does seem to be some confusion related to when the actual tax deductions expire. The current legislation expires December 31st, 2008, as we noted earlier in the broadcast. There is, however, some proposed legislation that could extend that deadline further, as well as possibly increasing the per square footage deduction that's available.
Great, thanks, Matt. Neil, the next one's going to be for you, and it is, you said that you can find energy savings even in new buildings. How do you do that if it was designed to meet current codes and standards?
Well, what we find in a lot of the buildings that we survey is that they've not been commissioned properly. A lot of times the buildings, all the equipment gets installed and the contractors will turn it on, turn it over to the customer, and without checking to make sure that it's meeting the actual design intent. So one of the large areas that we really find a lot of savings in is with the building automation system. A lot of times those systems are set up, they're put in, turned on, and the schedules aren't properly put into the software, and the systems themselves, the sequencing on the air handlers aren't working correctly. And we'll work with the customer and their building teams to fix these problems, put in the right schedules and the right control strategies. And typically we find an awful lot of savings from that. And this is with new buildings, which you would think, once they're turned over would be running optimally, but sometimes aren't.
Great, thanks, Neil. John, the next one's going to be for you, and it is, you mentioned that this was not a comparison of one system type to another. Why not?
Well, yeah, as I mentioned, the primary focus was to say if as a design team I'm leaning towards using a certain system type in a given building, what type of strategy should I implement to meet that minimum threshold of 2 points? If I was on the other side taking a design team more integrated approach and sitting back at the beginning and saying what systems are available given the constraints of the project and which ones should I use, I might look at it differently, which should be which system can give me the most EA Credit 1 points for a given budget, or which one can give me this many points at the lowest installed cost. And that brings in the installed cost variable, which we didn't include in this study for obvious reasons with different locations and different markets, things like that. We used it more as a focus on system type. So that's certainly a great analysis to do early in a project, but it wasn't the specific intent or focus of this one.
Thanks, John. We have time for, I think, one more question. So, John, I'm going to give this one to you. And it is, how does the LEED credit that requires 30% more outdoor air impact the ability to achieve EA Credit 1 points?
Yeah, there is a indoor environmental quality credit that gives you 1 point if you bring in 30% more outdoor air to the breathing zone. We didn't include that in this analysis, but if a design team chooses to go for that point, when they go back and do the analysis for EA Credit number 1, the requirements in Appendix G require you to use the same ventilation rates for both the proposed and the baseline. So in a sense, you really don't get penalized for it in that case.
Great. Thanks, John. I think that's about all the time we have for questions. And now it's time to wrap up today's broadcast with a review of the material covered. We'll follow up with written answers to all of your questions within a week or so. John, would you review the takeaways from the broadcast for our viewers?
Sure. The impact of any energy-saving strategy on the operating cost of a specific building depends on climate, building usage, and utility costs. And there are many strategies that can be investigated. Building analysis tools like TRACE 700 can be used to analyze these strategies and convert energy savings to real operating cost dollars that can be used to help make financial decisions about reducing operating costs, or to achieve LEED points under EA Credit 1, or to qualify for tax deductions such as the U.S. Energy Policy Act. Again, we strongly recommend design teams investigate these cross-cutting strategies like daylighting or shading to first reduce the load, then investigate ways to make the HVAC systems more efficient. Neil helped emphasize this fact by looking at several real-world projects where non-HVAC related strategies resulted in significant savings. And as Matt mentioned, we hope that the results from this example study will provide some guidance as to what energy-saving strategies should be investigated for the particular HVAC system that you may be leaning toward using on a given project. And really, any of these systems can be used on a LEED project. It's just that in some situations, load reduction strategies through envelope and lighting system improvements may be that much more important. Jeannie?
Thanks, John. As you could probably imagine, there are quite a few publications available with more information on energy-saving strategies. As Matt mentioned earlier, the results of this study are also published in the latest Engineers Newsletter that accompanies this broadcast, and a bibliography is available from your local site coordinator. It lists Engineers Newsletters, application manuals, and articles on this subject. Past broadcasts are available on tape or DVD, depending on the vintage. Please check out the Trane website for information on specific broadcasts. We have 2 more broadcasts scheduled later this year. We'll be back in September to cover the design and operation of small chilled water plants to provide insight into the long-term advantages of a chilled water system investment. And in November, Dennis Stanke and Mick Schwedler will be co-hosting with Steve Taylor, founder of Taylor Engineering, to provide design engineers with strategies to help design VAV systems that comply with both the ventilation requirements of Standard 62.1 and the energy requirements of Standard 90.1. We thank you all in advance for filling out an evaluation before you leave. Thanks for joining us today. We'll see you in September.